So we're continuing graph visualization. The last one I had, and I want to share the screen for now, so I'm not going to go to the slides directly, but last time we ended with looking at interactive level of details. So I have a few interesting techniques kind of going on. Node link diagrams. They're pretty much node link diagrams. And I just kind of want to show them to you, just FYI. So one of these was this interactive level of detail, kind of a way to deal with large graphs and not have a hairball necessarily. The next technique also tries to deal with large graphs. You can see here lots of intersections in the middle. So it's kind of a general, it's many ways of doing, but the main idea here is I want to bundle edges. So I want them to actually touch each other and reduce the number. So there's a lot of edges going from one area to the other. I want to bundle edges in that area and they kind of go together, just like almost think of it as the wires in a car, where they kind of, if they go towards the back of the car, they usually bundle them. As they get closer to the back, they unbundle them. They each go to different places in the car. So this is kind of the wire mesh that they're doing. There's a word, I keep missing it. But that's kind of the idea. And there's many ways to do that. There's a lot of math involved. Some of these involve some sort of ink base, so they look at the ink and try to reduce it. Others are based on energy, reducing the energy of the entire system by just bundling them, or having these, if two links are close to each other, they kind of, the energy, it's as if they're a proton and two wires, magnetic wires that kind of start clumping together. And there's a few more here based on images. So they do plain image processing, or they based on geometry, kind of go to 3D geometry. They have a grid geometry, or they kind of look like a tree. So there's more than one way to do it, and I just want to show you some of these techniques. Also notice at the bottom, like C in the bottom right corner, that's a parallel coordinate plot. So you can apply the same techniques that you would apply for a graph to a parallel coordinate plot to reduce, kind of, you bundle edges together. In other words, get rid of that hairball. They both suffer from the same problem. They kind of, lots of intersections potentially. So I'm going to play two of these videos. I don't think they have any sound. So notice there's a lot of intersection here, and now they're running the algorithm, and they're kind of getting closer and closer together. So now they bundle them. So that's the main representation they get. Here is the same thing. They're going to run the algorithm. It's most of, or I'm not sure if most of them, or at least the ones that I'm showing, are iterative. So you go through iterations and get them more bundled and more bundled and more bundled. So first of all, you have to figure out if you're bundling with the link to the right or the link to the left. That's one part of the algorithm. The other is the big bundle. Which path will it take? And that's, I think, maybe airline traffic or something along on the world. So that's one. I don't want that. This is kind of a continuation. So notice 150,000 edges. It looks like, I don't know what. Maybe the world. We've seen this one before. That's kind of the interactive level of detail. But in this case, they're bundling. They're not just changing level of details. They're just making the links kind of, they stick to each other. Kind of the same idea. You start to see big trunks. One thing to notice here is that links kind of tend to be bent. Oh, I didn't want to stay there. Even I mean, they do touch each other, but that's not the issue. The issue, kind of going back to tree graph visualization, they tend not necessarily to have the straightest path, so they will be more bent than usual. The intersections overall are reduced because each bundle doesn't intersect the other bundle as much. You can see there's virtually no intersection here between the big bundles. But the paths are no longer straight. So these are some of them. Like I said, this is based on, this looks more like a tree base. You can see that it starts from Los Angeles and kind of spreads out. One other interesting one is gene networks. We had a talk today that had heat maps from a gene and looking at gene expression. It's kind of the same idea. The reason I like it, it's because instead of having the normal node link diagram, they use more like an electronic circuit where you kind of, it's almost like you have current going through it and it touches in multiple places. So this way, instead of having 3 links going from one node to 3 others, you can just have one and it touches a little bit. And they have different ways of running this. So here is kind of the idea. For example, here I have C is connected to E and F. C is connected to both E and F. Because you can see this little area here. And also this whole pattern, B is connected to A. And then I'm not sure about that. B is connected to E as well, and F. So you can see how they reduced this whole kind of subgraph here, C, E, and F. They put it at the bottom and kind of reduce some of that. So here is how this works with a larger graph, and they have different ways of kind of shortening those or aggregate, selecting different nodes. I have that on Blackboard. Okay, let me stop for a second. 3, 2, 1. You can see there's a big gene pool right there. And you saw the heat map today. There's quite a lot of them. I mean, many, many. You can see the overall graph. And they kind of, if you go back to Taft, they're reducing some of the ink that they just or they can actually shorten some of the links instead of all looking like a matrix, they can shorten them. If they don't have to go any higher, they kind of stop. Once they make contact, they make contact. They can reorder these nodes here. Which would be a mess in a normal graph, if you would. And here is they can see all the pathways. They can see everything that's linked there. I think at some point they do some selection. They focus on a subset. So that's the subgraph that's connected to that R, GROK, whatever the name. And there is one more technique that's actually in the book. It's still node link technically because I can see nodes and links, but what they do here, there's no intersection. Here is how they accomplished this feat. I'm going to go back to the slides now. Because I can draw on it. So this is kind of worse in the 600 years between 560 and 7, between 500 and 700, in kind of where Great Britain is right now, and you see who attacked who. Green is red indicates the aggressor, I guess. So how come they have no intersections here? Well, the reason is they do repeat. So for this is the node actually, West Saxon. But notice for them they repeat the nodes. So if you kind of stretch out the graph, instead of having a single node for Saxon that's linked to everyone else, they won't be able to probably avoid intersection. Now what they did, they kind of duplicated that many times, and they avoided intersections. Now the links are not necessarily like if you compare the size of this link to the size of one of these, the variation is there. They're all straight, and so they can still vary, but they're straight and there's no intersection. And the other thing is they were able to add one more data dimension here, which is the time, one more attribute, so you can kind of see what happened over time. Yeah, so kind of it's still node link diagram. It's kind of interesting. The other one, I don't have it in here, but since we had it, a heat map can be a good representation of a adjacency matrix, especially if you have hundreds of thousands of nodes. Then each become a pixel, and you just color them. And that I found to be a pretty good representation rather than try. If you have thousands of nodes, easier that way. Just take the adjacency matrix and instead of 0, 1, make it white or blue, black. And you kind of see better. And on that part, it matters how you order the matrix. You get different patterns. But that's the end of node link diagrams. If you want to do, there's this tool called Tulip. If you want to use it, it's kind of research. So it's more for research. So it will crash on you if you do ever want to use it for something else. Make sure you save your results often. But it has a lot of the edge bundling. I think the first one might have been from Tulip. So it does edge bundling. It has a lot of built-in algorithms that you can use for a graph. And it does have scatter plots and other stuff. Parallel coordinate plots, you can plug it right in. So it's a pretty nice tool. I kind of have it there. And so that's the end of binary relationships. So when we talked about graph, we had edges and vertices. A vertex had exactly 2 edges inside of it. So if you think about tuples, what we had was a tuple with exactly 2 things, vertex 1 and vertex 2. Now, if I have a relationship that has more than 2, then that's kind of a general it's not a binary relationship anymore. So how do we visualize something like that? So in this case, for example, there's A through G are hotels. How many? There's 2, 4, 6, 7 of them. But then the swimming pool puts A, B, C, and D in a relationship. So I need to show that they belong to that relationship. Golf courses puts A, B, E, and F in a relationship. And restaurant kind of looks like A, C, E, and G in a relationship. Notice that I could have looked at this data and said, these are data attributes, but I can also look at it. It kind of going back to homework 1. Does it support GPU? Yes or no? But everything that supports GPU, you can think of it as being part of one relation rather than one data attribute. So It's really the same data, but the way we interpret it, we interpret them as being in a relationship rather than having a certain attribute. So it's kind of a slight, what should I say? It's a different way of looking at the same data. Instead of saying, oh, the hotel A is yes, yes, and yes, I'm going to say no. Swimming pool defines one set of relationship, one relationship. Golf courses, it's another relationship. So I look at them as tuples. But keep that in mind. For the project, may actually be helpful if you sometimes look at the data and say, what if I interpret it some other way, rather than just plain vanilla. These are data attributes. These are the entries. So how would I visualize something like that? One example: Venn diagrams. So hotel A has everything. That's why it's kind of in the middle. And then you can kind of see that B has swimming pool and golf course, but it doesn't have a restaurant. And so forth. So if I have more than 8 hotels, I can have each and every element. And that's the idea of a Venn diagram. Now there's Venn diagram, there's Euler diagrams, EULER. I'm not sure, but apparently the distinction there is a Venn diagram shows all possible combinations of the sets, while an Euler diagram doesn't have to show. So for example, there's something is missing, I don't have to show that representation, that part of the diagram. This one shows everything. So if you look at it, on this outside, I can actually have a dot here, a hotel that has nothing. And then I have a hotel that has everything, and then these are singles, these are doubles, and so forth. How would you do it for 4 of these sets? Right now I have 3 sets. Let me share the screen. It gets pretty, so for example, this first one, it's not a Venn diagram. It does have 4 sets, but it doesn't show all possible combinations. So let's look at it. Let's look at blue and purple. It doesn't show a combination where I only have blue and purple and nothing else. It shows a combination where I have blue and green and nothing else, but not all. So kind of if you go across, you don't find that combination. So that's not a Venn diagram. That would be an Euler diagram because it doesn't show all possibilities. And as you can imagine, possibilities increase. This one here is one that can show all possibilities with 4. And no, if I try and do 5, it starts to look something like this. And I'm not sure if this one does show all possibilities, but maybe it does. I have E and A. I don't have E and B really alone. So the problem is kind of showing across the middle area. Do you see an E and B? No. So it gets hard and not as intuitive even visually. So it works with 3, it works with 4, 5, 6, 7. How about 10? Almost never. I mean, what are all the possibilities? Think about. You have all those combinations, and there's thousands probably of possibilities. And I also have a video, kind of also related to Venn diagrams. I have a video of you can actually implement a tool. And this is more of a sketch. They didn't really implement this one. They kind of animated a sketch. And here they're looking for, I think, bonds or stock, one or the other. So you can see whether, oh, it's bonds. So international, US government, UK government, different types. You can do some selection here. And then you can look at the percent that you're getting from it, how long is the bond, and so forth, credit rating. So based on these, they would use a Venn, well, I don't think it's a Venn diagram. Now it's more like an Euler because it's not showing any possibilities. They call it Venn anyway. So they're going to use that to kind of allow me to visualize what I have there, what's the common things that I can find, and kind of explore that data set that way. And again, this data set is really, if you look at it, you can do it with a bar chart as well or some other visualization tools, but this is just using sets and relationships to look at data. So they selected based on currency type, their 1400s, credit rating. You can see there's some of them that are on different currency types. Now they're going to go and expand their credit rating and kind of start to see things where they intersect. So this is USD denominated or Japan. So they click here, and based on that, normally you would go to the results or drag it to the results and analyze them some more. But it's kind of looking at, you can do 3 of these. Obviously, you could do 4. After that, you're in trouble. So that's a Venn diagram. How would that be implemented? And it's probably doable. You can program it and have it running. The other thing I'm trying to do is minimize the amount of time I move back and forth, but it's just I have more and more demos. Another, this is also a Venn diagram, but they kind of, they call it info crystal. They make it look like a crystal. So you can see how they took each part of the set and made it more like a diamond or make it look like a crystal. I have not seen this in action, but it's kind of just making it more computer friendly, where the shapes are more predictable. Upset, let's look at it. This actually has a demonstration, so I will get back to it after this. Here is something they use the cluster map, again going back to the hotels having swimming pool and golf courses and restaurants. I don't know how you would do this with computer, what algorithm you would have to use if you have more than 3. Because here are the hotels that have restaurants, but not a golf course or a swimming. These are intersections there. You can kind of see the intersections. Again, once you get 3 or 4 of these, you would have so many of these veins that have to intersect. And again, I don't know how you do it, how you would write an algorithm for it. But that's another idea how to kind of, again, show relationships. Next one, parallel sets. So again, I have a small number of sets, and if you look at it, if I only have 3 sets, and if I try to do a scatter plot, they would look something like this. I have no matter what I do, they will be pretty far apart, and I won't be able to see necessarily a lot of information there. The same thing with parallel coordinate plots. I'll only have 3 points where they start. So again, they will tend to look like that, almost no matter what the relationship. So they say these two ways of representing data, scatter plots, parallel coordinate plots, not really work when I have a small number of sets. In this case, they have 4 sets, A, B, C, D. So what they propose is these parallel set interaction. And these are the Titanic kind of information. So you see at the top is the class, so first class, and how many people survive, and well, I guess It's the opposite. This must be first class. It's too small for me to read it. So this is first class. You notice that quite a few of them survived. Some of them did not. And then all the other classes, they kind of went to no. And then I'm going to use my magnifier here. Then you have men. Most men did not survive. Women did better. So in this thing is that's the parallel set. Next, they describe different interaction techniques. For example, on this one, they just reorder these two to make it look a little bit, to look for different information. On this one, they combine two of these. So you can see that they combine the second and third class together and kind of see what happened there. And you can explore what happened with men and women. In this case, there's not that many sets, as you can see. Next, they're eliminating part of it and looking at the rest. That's what they're doing here. And finally, I think they're just clicking on this one here. But I don't understand exactly what's happening there, but that's another interaction technique. So it's a way to look at sets. So I found this to be kind of, maybe it's the original. However, there's a bunch of them that have the same kind of arrangement. So parallel sets is the one I discussed, but then there's something called a Sankey diagram, and it looks like that. You can see it's the same idea, or alluvial, like river diagram. You can see where the data flows. And actually today, in today's presentation, there was one that was circular. It was called the chord diagram. It looks like one of these, except that's on a circular, kind of going back to lecture 2, looking at a spatial substrate. Well, that's just a round spatial substrate for a Sankey diagram that just goes between two sets. So it doesn't go through multiple. This one splits once. It may split multiple times. You can see that these here, they split multiple times. It looks like no male from, oh, there's someone that survived. Few males from the second class there survived Titanic. So that is the Sankey diagram. It's a way to look at sets and relationship between sets. And some graph visualization tools that I will not cover. If you're interested, the most popular ones, GIFI is pretty stable, and I've seen it used by people. Tulip has a lot more features, but it's a little bit slower because it has a lot of features. And it may be a little bit unstable sometimes after a long session. Well, after a few operations, you may want to save the work. But it can do quite a lot. And the last thing that I have is upset. Which may be the best one in terms of looking at data sets that have a lot of sets in there. So the idea here, you can see, for example, you can see the blue area. It's going to be represented by nothing, nothing, nothing. So it's all gray, gray spots. Only A, or rather only B, this is kind of the second one here. So if I have only B, I have a full black circle, and A and B are not included. Then if I have the intersection between A and C, you can kind of see it here. I have a line, and that shows the intersection between those two sets. So their metaphor is to use these dots and then kind of use lines between them. And then the one right in the middle is going to be all of them together. If I want to look at everything that A has, which means the A circle, notice that the A circle also has parts of B. parts of C, and parts of B and C. So that representation will have full A, so the entire set A is included, but I have a little bit of B and a little bit of C. So that is how the entire set A is represented. Notice that if I only have a circle on A, it means I have nothing from B and C. So it kind of, it's not the entire set. So kind of keep that in mind when you look at it. And they can do aggregation and all that. And there is a video. On top of that, you can look at other, just like Tulip, they have other charts in there to help explain what's going on, kind of see distributions. They have lines that kind of show the, again, frequency and so forth. And there, I have a video for it. Let me see, where is it? It's probably on Blackboard. No, it's on YouTube. So I will have to share the screen again. Last time this lecture, this set of slides, because there's nothing else I want to cover other than offset the video at the end. And while this kind of keeps going, I'm going to copy. Like I said, to me, this is the most complete one in the sense that you can look at many sets and combinations. You can go past 4 or 5 or 6.
Documentary.
Sorry, I jumped all the way at the end. Okay, so starting in 3. Oh, actually, before.
Sets are a common form of data. Suppose we have a set of characters that go to Springfield Elementary School.
Going back to the beginning, I just want to make sure I'm sharing the screen and not have surprises tomorrow. Okay, so 3, 2, 1.
Sets are a common form of data. Suppose we have a set of characters that go to Springfield Elementary School and another set of characters that work at the nuclear power plant. You might ask yourself, are there more evil people in a power plant or in school? Such datasets are often visualized with Venn diagrams. Venn diagrams are, however, not good at visualizing quantitative data, and they're really bad at visualizing many sets. What if I also want to learn about whether the characters have blue hair or like Duff beer? To do this kind of analysis, we have developed Upset. Upset uses a matrix to identify the segments of a Venn diagram. Each set is in a column. Each intersection is in a row. You can see the corresponding segments by hovering over the row. These are all the characters that are in school but not evil and don't work in the power plant. These are the characters that are evil but not in school and don't work at the power plant. And here are all the evil people that work at the power plant. The bars on the side show how big this intersection is. Clicking on one of the bars shows the contained elements in the table. We see Mr. Burns and Smithers as the evil characters at the power plant. We can add more sets by clicking on the label. Upset is designed to answer questions in a task-driven way. Sorting by cardinality helps you find the largest intersection. Sorting by deviation reveals the intersections that are larger or smaller than expected. Sorting by degree shows the intersections with low degree first. As you can see, the matrix quickly fills up. To deal with this, we can hide the empty intersections. For many tasks, it is helpful to aggregate intersections. You might want to know which sets intersect frequently with the school set. To do this, we aggregate by sets. This aggregation shows us that there are 6 characters in the school set. The biggest intersection in the school aggregate is school and male. However, there are other intersections that also contain school and male. To see the overall relationship between school and male, we can add an aggregation by overlaps. Here we see that there are 3 intersections in the male school aggregate, with a total of 5 characters. To get an overview of all interactions, we can hide the individual intersections. We can also explicitly query for an intersection. Let's select the males that work in the power plant. We see the 2 intersections and a total of 5 characters match our query. Set also visualizes elements and attributes. To demonstrate this, we've loaded a dataset about movies that contains movie genres, release dates, ratings, and popularity. The view here is aggregated by sets. Here we can see box plots of the attributes: release date, average ratings, and times watched. In the element view, we see a scatter plot of release date versus ratings for the whole dataset. It seems like ratings in the past were higher, but this is possibly a bias of the data collection. You can see that the number of movies in the sets is quite different. To get a better understanding of the size of the smaller bars, we can adjust the scale. Bars that break the scale wrap around themselves to keep them comparable as long as possible. Let's take a look at the documentaries. The box plots reveal that documentaries are rated higher on average than other genres. Documentaries also don't seem to mix much with other genres. Selecting their element reveals that most documentaries are recent productions. The war genre, which is also highly rated, contains a lot more classics. Looking at intersections, we see that war movies are more often of multiple genres than documentaries. We hope you enjoyed our tour of Offset. Thank you for watching our video.